good cloudy evening and a very warm welcome to the black hole. Perhaps the most frequently sought intellectual wish is understanding the nature of infinity. और जैसा कि अकबर अलाहाबादी कहते हैं कि तूले शब फिराक ज़रा नाप दीजिए। और इस दिलचस्प मौजू पर गुफ्तगू के लिए वी हैव अ गुड न्यूज़ एंड दैट इज़ कि जॉर्ज कैंटर जो हैं उन्होंने he made the most significant attempt in this direction, that is understanding the nature of infinity. मुझे बिल्कुल नहीं आइडिया कि कैंटर ने क्या काम किया और कैंटर्स पैराडाइज क्या है. आई एम एज क्यूरियस एज ऑल ऑफ यू एंड वी आर हैप्पी टू हैव डॉक्टर सरमद अब्बासी विद अस. मैं बस मुख्तसर सा उनका तारुफ करवाता जाऊँ. गुज़िश्ता 2-3 दिहाइयों से आप तहकीक और दरस व तदरीस से वाबस्ता हैं. साइंस और साइंसी शोर और ख़ास तौर पे रियाजी और मैथ से मुतलिक जो लेक्चर्स हैं उनमें बहुत सरगर्मी अमल है. 2 इनिशिएटिव काबिल ज़िक्र हैं उनके. ख़ास तौर पे एक आपका यूट्यूब चैनल है दैट इज़ नेम्ड मैथ कैट दैट एम्स टू प्रमोट मैथमेटिक्स एंड थ्योरेटिकल कंप्यूटर साइंस. मोर ओवर वी आर वेरी ग्रेटफुल टू हिम कि वो हर माह के पहले जुमे को यहाँ द ब्लैक होल में अपना कोई ना कोई टॉक जो है वो रखते हैं. आज किसी वजह से वो यहाँ पर इस्लामाबाद नहीं आ सके, लेकिन वेरी काइंड ऑफ हिम कि वो जूम पर हमें ज्वाइन कर रहे हैं. तो बस इससे पहले कि हम ये गुफ्तगू शुरू करें, प्लीज़ हमेशा की तरह एक फ़ेवर दीजिएगा कि अपने सेल फोन जो है वो साइलेंट मोड में कर दें सो दैट देयर इज़ नो डिस्ट्रैक्शन. आप ज़रूर इस गुफ्तगू में शरीक होइएगा और इंटरेक्ट कीजिएगा सरमद अब्बासी साहब से, बट जस्ट रेज योर हैंड फर्स्ट ताकि आपको ये माइक्रोफोन दे दिया जाए और फिर आपकी आवाज़ जो है वो ऑनलाइन ऑडियंस तक भी जाएगी और डॉक्टर सरमद तक भी जाएगी. बस यही थी 2-3 बातें. आप लोगों की आमद का शुक्रिया. नाउ प्लीज़ वेलकम डॉक्टर सरमद अब्बासी दो ऑन Zoom. Thank you.
Thank you. You're so kind of you, and thanks to all the audience. It's wonderful to see you. I wish I was there, but चलिए आज technology को use करते हैं. So I want to start with a little personal story of mine. So here is something, this is actually a book that I have framed, and it's it's in Sindhi. It's titled Galileo, and it's actually Life of Galileo translated in Sindhi. And I read this book when I couldn't read English properly, and I also couldn't read Urdu. And one of the great things that the old scholars, classical scholars from Sindh, they did was when they came back after their studies from abroad, they started translating a huge amount of literature. Okay, and this book has had a very profound effect on me. So, and I'll relate it to today's topic also. Here are some of the other books that I have collected on Galileo. I think this particular one was actually recommended by Pervez, and Galileo's story moved me so much that it's really had a very profound effect on my life. And today's talk, I'm going to start with something that Galileo did. It is from his book called The Dialogues, and there he presents a paradox. And the paradox is this: he writes 1, 2, 3, 4, 5, 6, 7, 8, and the positive integers. And then below that, he writes the perfect squares. And 1 is a perfect square, 2 and 3 are not. 4 is a perfect square, 5, 6, 7, 8 are not. And 9 is a perfect square, and then 16, and so on. And then he says, surely there are more perfect squares then or more positive integers. I'm writing it backwards. Positive integers, okay, then perfect squares. Okay, and that makes sense, because if you look at the list of perfect squares, there are things that are missing in there, right? In fact, they become sparser and sparser. But then he does something strange in his book, and he writes, now let's write down the positive integers Okay, and let me write down the perfect squares in a different way. Let me write down 1 squared, and instead of 4, I'll write down 2 squared. Instead of 9, I'll write down 3 squared, and 4 squared, 5 squared, and so. Okay, so I can take every integer and square it, and I get a perfect square. So surely there's exactly as many perfect squares as there are positive integers. Okay, there is a one-to-one correspondence between them. So this thing is called the Galilean paradox. And it wasn't resolved by Galileo. Actually, I think Galileo got really busy in his life after he wrote the dialogues because, you know, he was fighting for his survival. There was a trial of him, and the church was on his tail. Okay, so this is an amazing paradox. So the question is, are there more perfect squares, or are there more integers than perfect squares or not? You know, what's the resolution to this paradox? In the same book, he has another nice picture, which is very simple. It's 2 circles, right? And he says, surely the bigger circle has more points on it. Okay, and that seems very intuitive, right? It's bigger. But then he says, well, let's put a point at the center and consider this outward going arrow. It hits a point at the small circle and it hits a point at the larger circle. So I can map this x to f of x using this. And this way, it seems that there are exactly as many points on the smaller circle as there are on the larger circle, right? So this is the paradox he presents in his book, and then he doesn't touch the problem. Okay, and this is then later on taken up by Cantor, who started investigating infinity. Okay, so what is Cantor's idea and how does he investigate it? Okay, so here is something that we want to do. We want to actually count how many things are there. That's the basic question that we want to ask. But there is a even more fundamental question that you can ask. You can say, if I have 2 sets, do they have exactly the same number of elements in them? Okay, do they have the same, is their size the same? So there are 2 ways to do this. Okay, one is, so let's say you have a bus, okay, and you have children, right? Okay, right, so you have children and you have seats in the bus. Okay, and the question you want to ask is, are there as many children as the number of seats? Is the number of seats in the bus the same as the number of children? Okay, and there's 2 ways you can go about it. One is a very easy way, the way we do it, and the other will be Cantor's way. So the easy way would be that I'll go and count the number of children, and then I'll go into the bus and count the number of seats. And if the number comes out the same, then I'll say yes, otherwise I'll say no. It's very simple. But there's another way of doing it, is what you do is you tell the children to go and sit on the seats. Okay, and what do you want? Every child should get a different seat. You know, 2 people should not be sharing the seat. And the second is that if every seat gets occupied, right, then you would be convinced that the number of children is the same as the number of seats in the bus. Okay, so in this case, we have a set which is children and we have a bus. Okay, and what we're doing is we're mapping the set of children into the seats in the bus. Okay, and what we want is this function to have 2 properties. One is it should be 1-to-1. Okay, and what does that mean? Let's recall that. Most of us remember what it means, that if you have 2 different elements, then their function values should be different. Okay, so if x is not equal to y, that should imply that the function value of x is different from the function value of y. In the analogy of the bus and the children, what you're saying, if there are two different children, they get to sit on two different seats. Okay, so this is one thing that you want, and the other is you want this function to be onto. Okay, and what does that mean? Well, that says that every seat should be occupied. Okay, so for every y in the bus, there is some child, okay, such that f of x equals y. All right, so that just says that every seat has to be assigned, right? If I can find such a function, then I will say that these two sets have the same. Okay, so it seems like a very roundabout way of doing things. But the big advantage it has is that you can apply this test on infinite sets. Okay, whereas the first method would not work for the infinite sets. You can't just start counting the integers and then start counting the perfect squares. And what will happen is you'll never end counting the integers. So that method would not work. Okay, but with this method, you can compare infinite sets also. Okay, now the thing is, what is the consequence? Okay, so let me write down that definition. And that is the greatest accomplishment of Cantor's idea, that we say that the size of A is equal to the size of B if there exists, okay, a function f from A to B, which has these two properties, which is 1 to 1 to 1 and on to. By the way, a one-to-one function is sometimes called an injection, and an onto function is sometimes called a surjection in mathematics. But nowadays, this terminology is getting more standard, at least in my area. Okay, right. So the thing is, here is a definition, right? And at this point, what you can do is you can ask whether you like this definition or not. Okay, if you do like this definition, if you accept Cantor's definition, life is reasonably simple. You know, you take the next course in set theory and so on, and you can study the mathematics literature around you. If you don't accept it, right, then you have to come up with your definition. All right, and people do that. You know, there are people who spend their lifetimes, you know, redefining things and developing different theory. Then you'll get a different theory. Okay, so really we have to accept this definition if we want to study what Cantor did. Okay, so what is the consequence of accepting these definitions? So I had the positive integers, so the natural numbers, which is 1, 2, 3, and so on. And then I had the perfect squares, let's call it P, okay, which was 1, 4, 9, 16, and so on, okay? And now I can write down this function for you, which maps I to I squared, okay? All right? So here's a little function I've written for you. It goes from positive integers and it gives you a perfect square. And you can check that this is 1 to 1. If I is not equal to j, then their squares will be different. Okay, I squared would be different from j squared. And every square gets hit. So it's onto function also. Right? So now if we accept Cantor's definition, we will have to also accept that there are as many natural numbers as there are perfect squares. Okay, this is a consequence of this definition. All right, so in some sense, the Galilean paradox has been resolved. Okay, the two statements that Galileo had, one saying that there are fewer perfect squares, and the other one saying, no, they are the same as the number of natural numbers. The Cantor's answer is, well, this is the case, not the other way, if you accept his definition. Okay, all right. So when we start thinking about infinity, and the first infinite set that anyone thinks about is the natural numbers. 5, and so on. Okay, so this is the first time we encounter infinity. Okay, so there's a little story of mine. I don't know, I was very young, and when we were young children, we used to ask each other that aapko kahan tak ginti aati hai? So somebody will say, I can count till 50, I can count till 100, I can count till 500. And at some point, I realized that I could count, forever. I didn't have to stop, that there's a method in how you add one to a previous number. And so, मुझे याद है एक बार किसी मुझे कहा तुम्हें कहाँ तक गिनती आती है? So just to like brag, I told this guy lakh tak, okay? And the person said, okay, so now, okay? And it was a really embarrassing moment for you. So our first, this is the most natural infinite set that we think about, okay? And now we have Cantor's idea, which allows us to compare infinite sets, right? And therefore, we can ask a lot of meaningful questions. So for example, the most interesting question is there only one infinity? Okay, all right? Or is it possible to have a set which is strictly bigger than the natural numbers, who has more elements than the natural numbers? Okay, and we can ask very interesting questions. Okay, so one attempt that you can make. Okay, so let me write down a definition. Okay. Set, let's say A is called countable. Okay, actually countably infinite if the size of A is the same as the size of the natural numbers. Okay, all right. So if the size of A and the size of the set is the same, that means there is a function. So you have these natural numbers, okay, and you have this set A, and there's a function which is 1-to-1 and onto, right? So there is a 1-to-1 correspondence between your set A and the natural numbers. So in particular, the element 1 will be mapped to something which is A1, which we can call A1. Element 2 will be mapped to A2, and element I will be mapped to A. Okay, right? So I can actually write this set as something like A1, A2, A3, and so on. Okay, so a set is countable if there is a way of putting that set into a sequence. And the property of this sequence is it doesn't miss anything from the set. So you can say this is A1, this is A2, this is A3, and you can keep doing that. And if you're wondering, this list will never end. But any element in the set will eventually appear in the list, right? So that is what a countable set is. And now we can ask ourselves, are all infinite sets countable? Okay, all right, are all infinite sets countable? So one way to do that is, one way to try to answer this question is to try to come up with a bigger infinity. Okay, so try to come up with a bigger infinity. Okay, so let's do that. Okay. Let's try to come up with a bigger infinity. Okay. All right. So here I have to introduce this nice little thing. It's called the Hilbert Hotel. Okay. And it shows how naive attempts will fail. So Hilbert Hotel is a hotel which has infinitely many rooms in it. Okay, so there's room number 1, room number 2, and so on. So it's a countable hotel, but it's a countably infinite hotel. And there are guests in each room. So room number 1 has guest number 1, room number 2 has guest number 2, room number 3 will have guest number 3, and so on. And Mr. Hilbert, comes to the hotel and he says to the manager, can I have a room? And the manager responds that, I'm sorry, the hotel is full. Okay. So Hilbert replies to him and says, why don't you take guest number 1, move him in room number 2, take guest number 2, move him in room number 3, take guest number 3, move him in room number 4. So take guest number I and move him to room number I plus 1. Okay, into the next room. And now the first room would be empty, and I'll just take that. Okay, all right. So this is what is strange about infinity. In some sense, you have created more room in the hotel. Actually, you could do something even more interesting. You can say that I'm going to move guest number I to room number 10 times I. Okay, so guest number 1 will go to room number 10, guest number 2 will go to room number 20, guest number 3 will go to room number 30, and so on. And, most of the hotel would be empty. All right. And so Mr. Hilbert can go to any room and live there, which does not end with a 0. Okay. All right. So what is the Hilbert Hotel tells us? That suppose you have a countable set, let's say A1, A2, A3, and so on, and you add an element to it, let's say X, which is not already there. Okay, so you add one more element to your set. The question is, do I get a bigger set? Okay, and the answer is no. And the reason the answer is no is this set is also countable. Okay, the way you count it is you don't start with A1 and write the set. Okay, because then you'll never get to X. So the trick is you start with X and then A1, then A2, then A3. All right. Okay. So the function that I'm telling you is that f of 1 is X and f of k is A of k minus 1 if k is greater than or equal to 2. Okay, all right, okay. So throwing in one element didn't really help us. Okay, so we can try doing something even more radical. What we can do is we can take two infinite sets and put them together and ask ourselves, do we get a bigger infinity? Okay, so let me say that I have one countable set A, which is A1, A2, A3, A4. Okay, and I take a second one B, which is B1, B2, B3, and so on. Okay, and I can ask myself, well, what about A union B? Okay, and to simplify life, let's say they are disjoint sets. Okay, is it countable? And the answer is yes, because the way you can count it is by going like that. Okay, so you can go A1, B1, A2, B2, A3, B3, and so on. Okay, right? So unioning two countable sets gives you another set which is countable. So somehow the infinity doesn't increase. Okay, all right. So what else could we do? Okay. So you can think about set theoretic operations. You can union sets. Well, you can take cross products of sets, right? Which is taking many copies of the set. Okay. So what about cross products? Okay, so suppose if I take a set which is countable, okay, then I can think about A cross A, right? The set of all pairs of that I can make from these elements of A, okay? So how would this A cross A look like? Okay, so for example, let me just avoid clutter. Let me take the natural numbers. So what does natural numbers cross natural numbers look like? And the thing is, you have 1, 1, 1, 2, 1, 3, all the pairs that you have which start with a 1. Then you have all the pairs that start with a 2. Okay? Then you have all the pairs that start with a 3. Okay? And you have pairs like that. So you have infinitely many such lists. Okay, so the first list is infinite, the second list is infinite, the third list is infinite. The kth list is all the elements which have the first component, which is equal to k. And you have infinitely many lists which are themselves infinite. So do you get now a set which is bigger, which is uncountable? Okay, all right. And so the thing is, you can say, well, let me try to go like that and count it that way. Well, that doesn't work because you'll never finish this row. Okay, so you'll never get to the things which are below. All right. But there's a very nice way to actually enumerate these pairs, which is you go on diagonals. Okay, like that. Okay. Okay. And so on. So if I were to list them, I'll say this is my first pair. Okay, so P1 is actually 1, 1. P2 is actually 2, 1. P3 is actually 1, 2. And this is the third pair, this is the fourth pair. So P4 is actually 3, 1. And so on. Okay, so that's a very nice way of enumerating all the pairs. Okay, so number of pairs of integers is also countable. All right, so that attempt sort of didn't really work out because we can you can count them in other ways if you want. You can go like that. Okay, that's also fine. That way also you will catch all the is there a question?
So what about the power set of the natural number? Again.
Yes, yes, of course, we're getting to that. Yeah, okay. Yeah. So somehow cross product didn't work, and so the next thing is what about the power set? Okay, and that is Cantor's great theorem. Okay, which is that the power set of natural numbers is not countable. Okay, right? Okay, so what that means is there is a bigger infinity. Okay, there is an infinity which is strictly bigger than the natural numbers. Actually, we will prove a much deeper theorem, which is that we will prove that the power set of any set, okay, has strictly more elements than the set itself. Okay, right? And this statement is trivial for finite sets. Okay, it is not very difficult, but it's one of the most brilliant proofs I think, ever written in mathematics. We will do that. But what does this theorem of Cantor do? Okay. This actually tells us a very deep thing, that the infinity in you can start with the natural numbers, you take the power set of it, you get a strictly bigger infinity. Now take the power set of that, you'll get a strictly bigger infinity. And then you take the power set of that and you'll get a strictly bigger infinity. Okay? So he has really created this paradise, infinitely many levels of, okay? So somehow infinity is, okay. So I'm prove this and similar to, and we'll see how they're similar. So let's look at a set. Let's call that set the set of all 0.
Sarmad, you are losing your voice. Can you move your microphone up closer to your neck?
Is that better?
Somewhat, yeah.
Well, let me see if my, is that better?
Yes.
Hello?
Yes.
Okay.
Now.
Okay, all right, okay. So the Cantor set is the set of all sequences that you can form from zeros and ones. So some of them I can write. One is just keep writing a 0 forever. That's a sequence. You can write 1, 0, 1, 0, 1, 0, and do something like that. You could write, for example, you could write the number pi in binary, okay, and you'll get an infinite sequence, and we know something about that sequence. It's never repeating and so on. We know that from real analysis. So the digits of pi, or bits of pi, I'm sorry, not the digits, bits of pi, bits of e, okay, so there are lots and lots of these 0, 1 sequences, and the theorem says that C is not countable. Is not countable. Okay, and the proof is by contradiction. Okay, so let's say somebody claims that they can count this set, Cantor set. All right, so then what will we tell them? Well, you have to put the elements of the Cantor set in one-to-one correspondence with the integers. So in particular, you will have to tell me what is the first sequence. Okay, what is f of 1, right? And it will be a 0, 1 sequence. Okay, and then you have to tell me what is the second sequence. All right, and then you have to tell me what is the third sequence, and so on. What is the kth sequence, and so on. Okay, and your function has to be one-to-one and onto. So in particular, all sequences must appear in your list. Okay, and now what Cantor does is he creates a sequence that doesn't appear in this list, that's guaranteed not to appear in this list. And the basic idea is the first sequence starts with a 0. So I will put down a 1 there. So this way I made sure that the sequence is different from S1, okay, because it differs from it in the first bit, okay. Then I look at the second bit of the second sequence, and that's a 1 here, so I put a 0. So I made sure that this sequence that I'm creating will be different from S2, because it differs from S2 in the second bit. And I keep doing that. So I keep going down this diagonal, okay? And every time I see a 0 there, I put a 1 in my sequence. And if I see a 1 there, then I put a 0 in my sequence, okay? And now I can make the wonderful claim that this sequence C does not appear in this list, okay? And what is the argument? Well, if it appears in this list, then it must have been S of k for some k, right? But by construction, S of k and C differ on the kth bit. Okay, because if I saw a 0 there, I put a 1 in my sequence. And if I saw a 1, then I put a 0 in my sequence. For those of you who like formulas, C of I is just 1 minus Si. Okay, so this is S11, S12, and so on. Okay, so this way I have proved that the set of all sequences, 0, 1 sequences, is not a countable set. Okay, let's see what really that means. For those of you who know and like binary, if I take a 0, 1 sequence, okay, then I can put a dot in front of it and I can read this sequence in binary and it will give me a number. Okay, so every sequence gives a real number in the interval 0, 1. Okay, all right. So the set of all sequences, 0, 1 sequences, is in one-to-one correspondence with the set of all numbers, real numbers from 0 to 1. Okay, there's a little technicality there, but okay. So that tells us that the real numbers between 0 and 1 are strictly more than integers. Okay, so there are more, strictly more real numbers than there are integers. Okay, all right. Let's talk a little bit about something that I had promised. We can also talk about rational numbers. Okay, we can ask the question, well, how many rational numbers are there? Okay, so we realize that natural numbers are strictly smaller than, let's say, real numbers between, let's just say real numbers. Okay, so real numbers is a bigger infinity. Where does rational numbers sit? Okay, are there as many rational numbers as natural numbers? Are there more of them? Or what is the situation there? So what's the guess? Yeah.
Rational numbers will be equal to the natural numbers, right?
Yeah, and we've already proved that.
Yes, using the cross product of the sets, yes.
Yeah, okay. Remember that if you look at pairs, if you have a pair ij, right, then you can think of this as a rational number I over j. Okay, all right. So since the number of pairs of natural numbers are countable, therefore the number of rational numbers must be also countable. By the way, in this, so for example, there is a little technicality here, like 2 over 3 is the same as 4 over 6, right? So rational numbers actually have many representations. A particular rational number can have many representations. But what you can do is you can take the pairs. Okay, so you have pairs 1, 1, 1, 2, 1, 3, and so on. 2, 1, 2, 2, 2, 3. And remember how we enumerated them? We were going like this, right? Okay, all right. So in this list, what will happen is you will have 1, 1 that corresponds to the rational number 1, and you also have 2, 2, which is also 1. Okay, so there are repeats in this when you look at it from the rational numbers point of view, but you can always skip the repeats. All right, so that tells us that rationals are also counters. Okay, all right. Let me do one thing that I had promised in the abstract, which was that there's a very nice way of enumerating rationals. Okay, and the way you do it is you start with the rational number 1 over 1, okay? And you grow a tree, okay? So this will have two children. One of them would be 2/1, and the other one would be 1/2, okay? All right, so in general, if you have a node which is R/S, it will have two children. One of them will be R plus S/S. Okay, so you add the numerator and the denominator, and you put that as the numerator, you don't touch the denominator. And on the second side, you do the opposite. So it'll be R/R plus S. Okay, all right, so that way, what would go here, I guess this will be 3/1. And what will go here, it would be 2/3. Okay, and what will go here, it would be 1/3, and this would be 3/2, and so on. Okay, and this is enumeration by Calkin and Wilf. Okay, and the nice thing about this is that you can show that in this tree, every rational appears exactly once in its reduced form. Okay, all right, so this is a very nice enumeration of the rational numbers, right? And each one of them appears exactly once, and it's always in their reduced form. Okay, all right, so therefore what we have is that rationals are also countable. Okay, all right. So let me ask you one question. So we have natural numbers, so that's an infinity, and sometimes this infinity is denoted by this letter called aleph null. Okay, and then we have real numbers, okay, and its cardinality is denoted by C, and C stands for the continuum, right? Okay, so we have it, and we realize that there are more real numbers than there are rational numbers. Okay, so we have two different infinities, right? One is rationals, one is integers, rationals, and the second is real numbers. So one of the very interesting question is there anything in between? Okay, can you create a set which has strictly more elements than the natural numbers and strictly less elements than the reals? Okay, all right. Can you create an infinity which is in between? Okay, so for people who vote that yes, let's see a show of hands. Oh, okay. Because all right, so Shahryar says that infinity in between can be created. All right, other people say no, and the answer to this question is very beautiful. The answer is Shahryar is right, and everybody else is also right. Okay, all right. The answer is a maybe, a very strange maybe. Okay, so this problem of creating or thinking about an infinity which is in between these two infinities, this is one of the great problems. It's called the continuum hypothesis. All right, the continuum hypothesis said that between these two infinity there is no infinity, and great mathematicians tried to work on it. It was eventually resolved by two huge people. One of them was Kurt Gödel, okay, and the other was Paul Cohen, right? Okay, and what they showed was it's up to you. Okay, if you want to have an infinity in between, you get a mathematical system which is consistent. Okay, and you can do that kind of mathematics. If you assume the negation of the continuum hypothesis, right? Still you get a mathematical system which is consistent. Okay, so it's one of those lovely examples that people think that in mathematics things are always the answers are always crisp. Okay, they are yes or no answers, right? But mathematics does have maybes also, and they are very, very precise maybes. Okay. Okay, all right. So let me do one thing and then we can uh, discuss. Okay, so let's prove this Cantor's theorem. Okay, which says that for any set S, the power set of the set is strictly larger than the set itself. Okay, all right. And this statement is trivial for finite sets. Okay, so for example, if you take the set 1, 2, 3, 4, 5, let's say, and you write down all its subsets, right? You'll have to write down 1, 2, 2, 3, 3, 5, 1, 3, 5. There'll be the empty set there. There'll be the entire thing here. So you have lots of them, right? Okay. Right? So for finite, you can just count and see that these are different, but Cantor has to prove this for every set. All right? Okay? And so he can't really appeal to the finiteness of the set because he wants to do this for every set S.
Now,
Okay.
is this true
So-
for the set of all sets?
Oh, the set of all sets is huge trouble. Okay. Okay. The Zermelo-Fraenkel axioms don't allow you to talk about the set of all sets. Okay. All right. So there is a very beautiful story of. Thank you, Parvez. This is just a lovely question. Russell, right? That's called the Russell's paradox. Okay, if you talk about sets of sets, then you run into something called Russell's paradox. So let me do that and then we'll get back to this. Okay, so Russell said, think about a set, Russell said, okay, which contain all the elements S such that S is not an element of itself. Okay. All right. So Russell's set is all those sets which are not elements of themselves. Okay. And the question now Russell asks is R an element of itself or not? Okay. And the thing is, you run into trouble either way. If you say R is an element of itself, then by definition, it should not be. Because R only contains sets which are not elements of itself. Okay, if you say R is not an element of itself, then by definition, R should contain itself. Okay, so this is called the Russell's paradox. Paradox. So the set theory.
This comes from the Barber's paradox.
Yeah. So this is the Barber of Seville, okay? And the story is that Barber of Seville is a barber who lives in Seville, and he shaves all and exactly those people who do not shave themselves, okay? And the question is, does the barber shave himself or not? And either way, you run into trouble. If he does, then he shouldn't. If he doesn't, then he should, right? So that's a beautiful explanation by Bertrand Russell of his paradox. By the way, I very recently found out that Barber of Seville is actually a opera. Okay, so somehow I used to wonder why did Russell chose that particular name of Seville? Where did the town come from? And it's a famous opera, and So that's why I think he chose that name. Okay, so let's go to Cantor's theorem. What we wanted to prove is that the power set of a set is strictly bigger than the set itself. Okay, and let's try to spell out what it means. Okay, well, it means that if you take a function, okay, that maps the set to its power set, then it must miss something. Okay, that means otherwise you have put the set and its power set in one-to-one correspondence with each other. Okay, so let me write a little finite example. 1, 2, 3, 4, 5. Okay, and if you want to create a function that goes to this power set, okay, then you'll miss at least one thing. That's what we want, right? That you can never put them in one-to-one correspondence with each other. And here's the beautiful proof. So Cantor says, let f be any function which maps the set to its power set. And I will show you something which you missed. Okay? All right. So let's think about this function. So if I look at f of x, what is f of x going to be? What kind of animal it's going to be? Well, the range is the power set. So this itself is a set. Is a set. Okay, so for example, let's say this was your function. Okay. All right, and let's say 3 goes to the empty set and 5 goes to 1, 2, 3, 4. Okay, so when I take the function value here, I get a set, right? I get something. So this is a legal question I can ask. Is y an element of f of x? Right? That's a legal question because this is a set and this is something in my original set S. Okay, so this is a legal question. All right, so now what I can do is I can create this set, Cantor set, let's call it C, okay, which is going to be all x's such that x is not an element of its own image. Okay, so for example, how do I create this set for this particular example? I say 1. What is f of 1? That's 1, 2. 1 is an element of 1, 2. So that means 1 is not in my set. I will not put it in my set. 2, let's say, let's make this a little interesting. Say 2 is mapped to 3, 5. So 2 is not an element of its image, so I will put 2 in here. Okay, and similarly 3 goes to empty set, so it's not an element of its image, so I'll put 3 here. Okay, 4 I've mapped to 1, which is not, so I'll put 4 here, and 5 I've mapped to 1, 3, 4, 5, so I will not put that. So this is how this Cantor set is created. And now it is guaranteed not to appear in the image of S. Okay? All right? And why is that? That's sort of like the previous trick I did. See, it could not be f of 1 because f of 1 contains 1, and I made sure I didn't put 1 in here. Okay? It could not be f of 2 because 2 was not an element of f of 2, and I put 2 here. Okay, and it could not be f of 3 because 3 was not an element of its image and I put 3 in there. Okay, so in particular, it could not be f of s for any s in the initial set. Yes, there's a question?
How would you show, however, that Cantor set is at least non-empty in the case of an infinite set?
It could be empty. this set could be empty. Okay, all right. I'll tell you in which case it is empty. Suppose I happens to be an element of f of I for all I. Okay, so let's say you cooked up a function g, right, such that s was always an element of g of s. Okay, all right, then the Cantor set would be empty. All right, but the thing is, in your image, no set is empty. Right? So I've found you a set that you've missed, namely the empty set. Okay? All right? So if you want to convince me that these two have the same size, you have to give me a function which is onto. All right? In that case, you have to hit everything. Right? And if you created this kind of example in which I was always an element of f of I, then you miss the empty set. And Cantor's argument will pop that out for you. Is that okay?
Oh, yeah, perfect.
Okay, okay, all right. Okay, so this technique is called Cantor-Diagonalization. Okay, right? And so Cantor is the granddaddy of all diagonalizations. Okay, diagonalization is a very important trick, a technique that is used in mathematics, especially in mathematical logic and also in computer science and computability theory. The three great pieces of work are due to Cantor, okay, Turing, and Gödel. Okay, Cantor laid the foundation of set theory, right? He uses diagonalization to show that there are bigger and bigger infinities. Okay, Turing uses diagonalization to show that there are uncomputable problems. There are certain problems that no computer can solve. All right, there are problems for which you cannot write an algorithm. There are computational problems which are computationally unsolvable. And Gödel uses diagonalization in a very, very clever way to show what is called Gödel's incompleteness theorem, okay, which I can explain. So if you take a mathematical system in which you make some assumptions. So for example, if you're working with group theory, with groups, then group theory has certain axioms which groups satisfy. Similarly, you have number theory in which you make some assumptions. So once you make assumptions and you have a consistent system, all the statements that you can think about, okay, they are divided into two groups, one which are true and the others which are false. Okay, all right, and here are your axioms. Okay, and there are certain statements which are true, and you can prove them using your axioms. All right, and the deep question is every true mathematical statement actually provable? Okay, all right, is it true that if there is a mathematical truth, we will eventually reach it? Okay, and Gödel's great theorem is no, that's not the case. That's not the case for number theory. There are mathematical statements in number theory which we will never prove. And Gödel also uses diagonalization. Okay, let me tell you a little bit about these three people. Cantor died in a mad asylum. Okay, Turing committed suicide by eating a cyanide-laced apple. Okay, and Gödel starved himself to death. Okay, all right, and I don't know, these three great people had such tragic endings. I don't know why that is the case, but they had some made deep contributions to the thing. Okay, now let me just see something about what really frustrated Cantor.
I have a question in the
Yeah.
so पीछे आपने कहा कि statements true हैं और false हैं, यहाँ भी फिर language का problem है. What do you mean by true? True already अगर true है तो वो कोई proven statement है, तभी आप उसको true कह रहे हैं. On which basis you are saying that it is true?
Okay. Okay. So how to? So, for example, if you look at the Riemann hypothesis, which is a hypothesis in mathematics, right? And we don't have a proof of it yet, right? People just say that, oh, it is true. It's probably the most sought after problem in mathematics, right? Now, what might happen is we are not able to prove it because we are limited, okay? Human beings are limited. But there can be another reason why we might not be finding the proof, because there isn't a proof available.
So here by
Okay.
here by true and false you mean so valid statements just within the system?
Okay, all right. So let's take a particular example. So x to the n plus y to the n equals z to the n has no positive integer solutions. All right, this is called Fermat's last theorem, right? This statement we now know is true. Okay, all right.
What is the status of this before that? Is
Well, before that it was a conjecture.
okay.
Right? Okay. But the statement itself is either true or false. Right? Okay. Either you will be able to find integer solutions. In that case, this statement is false, or there aren't any solutions. Right? So the truth of this statement has nothing to do with the existence of its proof. Okay? A proof is a step-by-step procedure, right? Using rules of logic and the axioms, you conclude something. Okay? All right? So
a true statement can be a conjecture.
Yeah. And the question is, if it is a conjecture, will it always remain a conjecture? Okay? And Gödel's theorem says, yes, there are statements like that, which will never be resolved. And the reason they will not be resolved is not because humans are limited, okay? Because the proof doesn't exist. Okay? All right? For this, so if you go in logic, right, they use these two notation. One is this notation. This means a statement is provable. Okay? And they use this other notation. This means the statement is true. Okay? All right. Now, what logicians say is that if a statement is provable, all right, then it must be true. You can conclude that. Otherwise, your system is inconsistent. All right. Now, the interesting question was, does the implication go backwards? If the statement is true, does there exist a proof of it? And that's where Gödel comes in and he says that for sufficiently complex systems, consistent systems are incomplete. In the sense that there are statements which are true, but not provable. Yeah. And I could probably do a proof of Gödel's theorem in 2 hours, okay? And it's one of the most fascinating theorems. I mean, both in terms of its implications, its philosophical implications to mathematics and the techniques that he uses. It's a seriously a disturbing proof in some sense. When you understand it, you can't sleep for weeks. That's what actually happened to me when I studied it. Okay. All right, so now I want to talk about one last thing, okay, and that is the Schroder-Bernstien theorem. Okay, all right, let me write down a statement. Suppose if a set and see, from here, what do you want to conclude? Well, you will probably conclude this. Okay, if A has at least as many elements as B and B has at least as many elements as A, then they both have the same number of elements. Okay, and this thing is obvious for finite sets. Okay, this is a triviality for finite sets. Cantor wanted to prove this for all sets. Okay, all right, and it turns out that it's not easy. Okay, at least Cantor couldn't prove it himself, right? And it was later proved. So the problem is, if the size of A is bigger than B, then you have a function which goes from A to B, which is 1 to 1. Okay, and if this statement is true, then you have a function from B to A, which is 1 to 1. All right, and what you're trying to prove is you're trying to cook up a function h that goes from A to B, right, which is both 1 to 1 and onto. Okay, all right, okay, so if I read this out, what does this statement say? It says, if there's a function from A to B which is 1 to 1 and a function from B to A which is 1 to 1, then I should be able to put A and B in 1 to 1 correspondence. Okay, Cantor wanted to prove this, but he couldn't. Okay, it was finally later proved by two mathematicians, Schroder and Bernstein. And it's a very famous theorem in set theory. It's sometimes called the Cantor-Schroder-Bernstien theorem because Cantor conjectured it. Okay, so some things which are obvious in finite sets, you know, they are sometimes untrue for infinite sets. Sometimes they are true, but proving them can be quite a challenge. Okay, all right. So yeah, so it's what, 7:30. So shall we stop here and we can have a discussion and I can answer questions. Okay.
जी इट वाज वंडरफुल लेक्चर। अच्छा, मेरा चूँकि बैकग्राउंड थोड़ा सा मुख्तलिफ है, मैं मैथ से फ़िलासफ़ी की तरफ नहीं जा रहा, मैं फ़िलासफ़ी से मैथ की तरफ आया हूँ। तो मैं ये समझता हूँ कि फ़िलासफ़ी में ये सवाल पहले लैंग्वेज वालों ने एड्रेस किए और तकरीबन इसी नतीजे पे पहुँचे। मसलन जो विटगेनस्टाइन ने ट्रैक्टेटस लॉजिको फिलोसॉफिकस लिखी थी, वो प्योरली लॉजिकल उसमें लिखी थी, प्रेमिसेस में बाकायदा नंबरिंग के साथ, और एक प्रेमिस से फिर लॉजिकली वो दूसरे पे जाता है, और वो पूरी बुक उसमें लिखी थी, और उसका मेरा ख्याल है प्रेफेस शायद इसी ने, रसल ने लिखा था। रसल और बाकी मैथमेटिशियंस का ख्याल था कि लैंग्वेज में इम्परफेक्शंस हैं, इम्प्योरिटीज़ हैं, इनको अगर ग्रेजुअली दूर कर दिया जाए तो हम प्योर लॉजिकल रीजनिंग के बेस पे ट्रूथ और फॉल्सिटी को हम कम अज़ कम असर्टन कर सकेंगे। और हाँ, रसल और वाइट हेड ने जो है वो प्रिंसिपिया मैथमेटिकिया में कोशिश भी की। मैं वापस आता हूँ, विटगेनस्टाइन ने जो उसको सम अप किया था वो दो जुमलों पे किया था। एक तो उसने ये कहा था, इफ़ एनीथिंग कैन बी सेड इट कैन बी सेड क्लियरली, और दूसरा ये था कि वेयर ऑफ वन कैन नॉट स्पीक देयर ऑफ वन मस्ट बी साइलेंट। अच्छा, ये लिख के किताब उसने कहा कि बेसिकली जितने प्रॉब्लम्स हैं फ़िलासफ़ी के और ये पैराडॉक्सेस जितने भी हैं, दे आर ऑल लिंग्विस्टिक प्रॉब्लम्स। और लैंग्वेज को थोड़ा सा ज़रा ब्रॉडर सेंस में अगर आप लें तो एक आउटर वर्ल्ड है, हम उसका एक इनर मॉडल बनाते हैं टू मेक सेंस ऑफ दैट वर्ल्ड। वो पिक्चर भी हो सकती है, वो वर्ड्स भी हो सकते हैं, वो सिंबल्स भी हो सकते हैं, वो मैथमेटिक्स भी हो सकती है। तो शुरू में ये ख्याल था कि ये जो इम्प्योरिटीज़ लैंग्वेज की हैं ये जब दूर हो जाएंगी तो हम एक ऐसे सिस्टम में पहुंच जाएंगे जो फॉर्मल भी है और कंप्लीट भी है, ठीक है। लेकिन जो चीज़ लैंग्वेज वालों ने प्रूव की थी, यानी विटगेनस्टाइन आखिर पे इस नतीजे पे पहुंचा कि बेसिकली इट्स अ लैंग्वेज गेम। लैंग्वेज गेम का मतलब ये है कि जो सेट ऑफ एक्सियम्स हैं ना, जो रूल्स हैं गेम के, दे विल एक्चुअली डिफाइन वेदर अ स्टेटमेंट इज ट्रू और फॉल्स, ठीक है। तो एवरीथिंग एक्चुअली गेट्स मीनिंग फ्रॉम द रूल्स ऑफ दैट गेम विच यू आर प्लेइंग। तो उसमें गर्डल ने अगर एक एक्सियम इंट्रोड्यूस करवाया, या गर्डल ने जो है वो उसको कहा कि ये इंडिपेंडेंट ऑफ एक्सियम्स है, यानी जो पहले से एक्सियम्स मौजूद हैं उनके ज़रिए इसको कंटिन्यूम हाइपोथेसिस को साबित फॉल्स नहीं साबित किया जा सकता। कोहन ने कहा कि जी उनके ज़रिए इसको ट्रू नहीं साबित किया जा सकता। इसका मतलब है कि अगर आप एक्सियम कोई और इंट्रोड्यूस करवाएं तो इट विल एक्चुअली डिपेंड ऑन द नेचर ऑफ एक्सियम। जी
मैं
यानी वो इंडिपेंडेंट, अगर उनका रिजल्ट इंडिपेंडेंट है तो इसका मतलब ये है कि अगर आप उसका एक्सियम जो है वो खुद बनाते ही ऐसे हैं तो वो ट्रू भी हो जाएगा, वो फॉल्स भी हो जाएगा।
हाँ, so
तो ये लैंग्वेज गेम नहीं है क्या?
Look, I don't know much about the linguistics and language, but basic idea is Gödel shows you a Gödel statement, which is you have a system and it's not provable and it's true statement. So what you can do is you can add that statement in your system as an axiom. Okay? All right? The problem is when you do that, there is another statement which is true and not provable. So the game never ends. Okay? So you can find out systems and you can find out consistent things with it, and you can keep adding them as axioms. Whatever you say, oh, I can't prove this, let me just put it as an axiom. First of all, how would you figure out that it's a true statement? But let's say you could even do that. Even if you add it as an axiom, another problem is created. That's the beautiful Gödel's theorem, right? Yeah, but about language,
नहीं, ये तो ठीक है कि वो इनकम्प्लीट है, ठीक है, वो तो समझ में आ गया। लेकिन साथ ये भी है कि अगर आपने उसको सॉल्व करना है तो आप उसका एक्सियम एक ऐड कर दें, एक मतलब इसका ये भी तो है ना। लेकिन उससे वो मसला तो हल हो जाएगा, एक दूसरा मसला हल नहीं होगा, यानी कंप्लीट सिस्टम, फॉर्मल सिस्टम नहीं बनेगा। तो बेसिकली फिर ये लैंग्वेज गेम ही हुई ना, कि जिसमें आप उसके रूल्स जो हैं वो डिफाइन कर रहे हैं कि उनके ज़रिए आप उसको ट्रू को फॉल्स करार दे सकते हैं, फॉल्स को ट्रू करार दे सकते हैं। और ये जब विटगेनस्टाइन ने ये बुक लिखी थी, रसल के हवाले की थी, उसके बाद उसने कहा था कि आई हैव सॉल्व्ड ऑल फिलोसॉफिकल क्वेश्चंस, ये सारे के सारे जो हैं ये लिंग्विस्टिक प्रॉब्लम्स हैं। और वो तो खैर रसल फिर बाद में उसको पकड़ के लाया और उसको कहा कि भाई अभी मसले हल नहीं हुए सारे, तो दोबारा जो है वो उसको वो खींच के लाया, वरना वो तो छोड़ छाड़ के एक किताब लिखने के बाद उसने कहा मैंने फॉरएवर सारे फिलॉसफी के मसले हल कर दिए हैं इससे। लेकिन समहाउ एक लैंग्वेज की तरफ से जो बंदा आता है वो ये ज़रूर महसूस करता है कि जो ये तीनों लोग कह रहे हैं, एलन ट्यूरिंग कह रहा है, गर्डल कह रहा है और कैंटर कह रहा है, वो इससे पहले फिलोसफर्स जो लैंग्वेज से रिलेटेड है, मसलन एक और जो मेरे जहन में बड़ा नाम आता है वो हुसल का है ना, फिनोमेनोलॉजिस्ट जो था, वो कहता है कि ये कंस्ट्रक्टेड वर्ल्ड है हमारे दिमाग की, ये लॉजिकल कंस्ट्रक्टेड वर्ल्ड है, उसके अंदर रह के हम उसको प्रूव कर सकते हैं, ठीक है। जो बाहर है, खारिज में है, वो उसको कहता है वो नॉमिनन है, और जो हमने कंस्ट्रक्ट किया, खा वो वर्ड से किया, खा वो नंबर से किया, खा वो किसी भी मॉडल से किया है, मैथमेटिकल मॉडल से किया, वो फिनोमेनोलॉजिकल वर्ल्ड है, वो रियल वर्ल्ड नहीं है, वो नॉमिनोलॉजिकल वर्ल्ड नहीं है, वो फिनोमेनोलॉजिकल वर्ल्ड है. तो वट एवर विल बी एबल टू प्रूव, we'll be able to prove it within that phenomenological world, because we will never have a direct access to nomenon. हम उसको हमेशा मॉडल के ज़रिए ही करेंगे, और मॉडल की लिमिटेशंस भी हो सकती हैं, हमारे ब्रेन के फंक्शन करने की लिमिटेशंस भी हो सकती हैं. तो आई जस्ट वांटेड योर टेक ऑन दैट. मतलब ये मुझे तो ऐसे लगता है जैसे जो एक ड्रीम था कि शायद मैथमेटिक ऐसी परफेक्ट लैंग्वेज है जिसमें ये सारी इम्प्योरिटीज़ ये ख़त्म हो जाएंगी, या क्लोज्ड परफेक्ट सिस्टम होगा. वो ये जो आप डिप्रेशन कह रहे थे शायद इसी वजह से आता है, बिकॉज ऑल ऑफ अस एक्चुअली वांट टू सी द परफेक्ट कंप्लीट सर्कल, जिसमें परफेक्ट सिस्टम हो और इनकम्प्लीट ना हो और फॉर्मल भी हो. जी.
Yeah, I mean, I don't know much about philosophy and language, but मुझे शायद एक quote याद आ रहा है रसल का. He said that when he was young and he was very smart, he used to do mathematics, and then when he became a bit rusty and stupider, he started doing philosophy. And then when he became even more rusty and stupider, he started doing politics. Okay, so that's how he ranks these three things. तो मुझे तो इन तीनों इतनी अच्छी नहीं आती, लेकिन थोड़ी सी मैथ्स आती है, बाकी दो चीज़ों का मुझे ज़्यादा पता नहीं है. Yeah, but Gödel's theorem says that Russell's dream will never come true. You will never have a consistent, complete system. You know, you're doomed to you're doomed to live with incompleteness.
तो इसमें हम ये भी कह सकते हैं कि जो स्टेटमेंट है कि ट्रू स्टेटमेंट कैन बी ट्रू और फॉल्स, कैन बी प्रूवन और नॉट प्रूवन. तो हम ये रियल और प्रैक्टिकल वर्ल्ड के पॉइंट ऑफ व्यू से ये तो कह सकते हैं कि हम ऑप्टिमाइजेशन की तरफ जा सकते हैं, कि जो चीज़ हमारे लिए हमारे सिस्टम को सॉल्व कर रही हो, अगर हमें वो ट्रू लग रही है तो हम उसको अपने सिस्टम के पॉइंट ऑफ व्यू से उसको सॉल्व कर लें. इसके हवाले से आप क्या कहेंगे?
रियल वर्ल्ड को फिजिक्स डील करता है. फिजिक्स का गोल ही ये है कि टू अंडरस्टैंड द फिजिकल वर्ल्ड. You know, physics and the way they do it is they use very sophisticated mathematics. Of course, they make simplifying assumptions, but they are coming closer and closer to reality. I mean, that's what we have seen. Or the fact that they are coming closer and closer to reality is uska proof hai is technology. You know,
Exactly.
I mean, my cell phone works, and the amount of physics that has to be right in order for my cell phone to work is just amazing. It's spectacular, right? So that tells me that physicists know what they're doing.
तो हमने
but-
सेटिस्फाई होने के लिए ये कहेंगे कि हम अपने ऑप्टिमाइजेशन की तरफ चलते चले जाएं, ताकि हम उस इशू में ही ना रहें कि यार ये सॉल्वेबल या नॉट सॉल्वेबल या ट्रू या फॉल्स नहीं है.
देखिए, मैथ्स का जो है ना, what John Conway said that most people don't realize, but mathematics is a aesthetic endeavor almost entirely, right? तो मैथमेटिशियन तो ब्यूटी के पीछे जा रहे होते हैं. उनमें फिर होते हैं जो अप्लाइड मैथमेटिशियन होते हैं, जो रियल वर्ल्ड के करीब जाते हैं. आई थिंक probably the best applied mathematicians are physicists, you know. बट जो प्योर मैथ्स करता है वो तो उसके एलिगेंस के लिए ही करता है.
You know, one of the most amazing things that I find is that there are as many points between 0 and 1 as there are in a cube of infinite volume. Any volume.
Yeah, yeah, yeah.
Uh, And then you can go to a hypercube in n dimensions and
Yeah,
then make
yeah,
n go to infinity.
yeah,
So now forget 0 to 1. Between
Yeah.
0 and any number, no
Yeah.
matter how small, the number of points
Yeah.
is the same.
Is uncountable. Yeah,
So,
absolutely.
so the size of the sets is equal.
Yeah.
But how do you prove that?
Well, okay, so here's something which is very interesting. So there's something called the Hilbert curve, which is a space filling curve. Okay, so it's actually a function from the set 0, 1, okay, to the square, all right, which is onto, okay, and the amazing thing is that the function is also continuous, okay. So what that means is you can have an infinitely thin pen, and you can go around and fill an entire square with it, all right? And that's fascinating to me, that such a curve exists. However, if you insist that the function should be differentiable, okay, then such a function doesn't exist, okay?
No,
And mathematicians have proved it.
okay. So we're
So you'll have to go in a fractalish way.
the Weierstrass function
Yeah,
would for example, but the size of the sets, it's just mind-boggling. Forget 0 to 1. It can be even a
Yeah.
smaller interval than that, and
Yeah,
yet there are as many points as anywhere else.
yeah, yeah. Yeah, between any two real numbers, there are as many points as, so. Yeah. Any other questions?
Okay, Sherry.
Sir, so the truth of theorems depends on the axioms, right? The truth of any theorem, like the Pythagoras theorem. So that depends on Euclid's axioms. So if
Yes.
Euclid's axioms are true, then Pythagoras' theorem is true. So, for example, if we construct a different kind of mathematics, for example, in an alien world, a new kind of axiom system is assumed using their whatever intuition they have. So, can there exist an axiom system in which Pythagoras theorem is false or any of our theorems
Yes.
is false? Can that be the case?
Yes, absolutely. Actually, you people are doing it all the time, but there are, non-Euclidean geometries, right? Euclid का जो axioms हैं, उसमें they are consistent, right? And the biggest problem with Euclid's axiom was the fifth postulate, okay? And the fifth postulate says that if you take a line and a point which is not on the line, then you can exactly draw one line that is parallel to it through this point, okay? This was the fifth postulate. And people tried to prove it for a long time, okay? And the question was, is Euclid's fifth postulate true or not? And the answer is, once again, a beautiful maybe. That if you assume Euclid's fifth postulate, you get this geometry which you do on the plane, which we call Euclidean geometry. If you assume that there are more than one lines which are parallel, then you're doing something called spherical geometry, okay, which is on the, no. If you assume that there are no parallel lines, zero parallel lines, then you're doing geometry on the surface of the sphere, okay? And here points are points on the sphere and lines are the great circles. And all great circles intersect. So there are zero parallel lines, okay? And if you assume that there are more than one, then you're doing what is called hyperbolic geometry, right? Okay, then you're doing geometry on the hyperbola, and the sum of the angles in this world in a triangle is always greater than 180. In the hyperbolic geometry, it's less than 180, and it's always equal to 180 in Euclidean geometry. Okay, so you have these three different worlds. और आप फिजिक्स वाले तो यूक्लिडियन ज्योमेट्री कभी नहीं करते.
This
You
is
know?
something that we use daily, actually.
You know, yeah.
And
All
this
of
this
physics
comes
says,
from Riemann,
yeah,
who was driven mad by Gauss.
yeah.
Riemann
yeah.
came as
So-
an 18-year-old, and Gauss told him, "You try and prove that fifth axiom," and he couldn't. So he went back to his village, and that's where he had a nervous breakdown. But at the end of that, he produced that curve space geometry, which now every graduate student has to learn.
Yeah.
Yeah,
Physicists are
maybe
very
this
good
was
at
not
these.
a good example. I was just like I mentioned Pythagoras theorem as just an example. Obviously, it is not. It is violated in the case of general relativity and curved spaces. But what my main question was: does that apply to any theorem at all? Every theorem is any theorem which is true in our axiom system, any at all, false in some other system. So would that apply to Gödel's theorem as well? Or is that a meta theorem of some kind?
Okay, so if you have axioms and if they are consistent, right, then you can talk about a mathematical world. It makes sense about mathematical world. There's actually a very simple and beautiful theorem in logic, and logicians prove that. And that theorem says that if you have an inconsistent theorem system, in that system, everything is provable. Okay? All right? And that theorem of logic is very important because what it says is that if you take a mathematical system, one inconsistency will ruin everything for you. Everything will become provable. Okay? All kinds of nonsense will become provable. Okay? So if you have a consistent system, then only certain things are provable. And those are things which are true in that system. They have to be true. That's the definition of consistency.
So Gödel's theorem does Gödel's theorem depends on our axioms, or is it like independent of any axioms? Does it apply to any axiom system? So wasn't it proved using our own axiom system?
Okay, so Gödel proves that any system that contains number theory is incomplete. Okay, all right. You can have complete systems, right? If your system is very, very simple, every statement you could be able to resolve. You know, if your universe is so tiny, right, you will be able to prove everything which is true in that world. Okay, so the system, once the system becomes it's complicated enough to talk about numbers, then it becomes incomplete. Okay.
So there are theorems that are true for any possible axiom system. Okay. Sir, another question was that since the continuum hypothesis can be both true or false, has anyone ever constructed a set that actually its cardinality lies between the naturals and the reals? Has anyone constructed a set of that sort?
Okay, so some of these, the correct answer is I don't know. Okay, I don't. Now I might be wrong, but let me think about this. It would not be possible to construct a set because if you would have constructed the set, तो debate ही खत्म हो जाती ना. फिर ये दो answers नहीं होते. Okay, all right. So the two answers are is that you write this statement S, okay, which says there exists a set which is S, which is strictly between naturals and reals. Okay, let's give this statement a name. Let's call this statement R. Okay, now what logicians have proved is that this statement R is consistent with the axioms of set theory. The negation of this statement is also consistent with the axioms of set theory. Okay, so you get two different branches of mathematics, one in which you assume the continuum hypothesis and one in which you can assume its
Yes,
negation.
so I am asking about the mathematical system in which you can construct such a set. So this is just like what we discussed about non-Euclidean geometry, right? So there is one system in which fifth postulate is true and other system in which it is false. So the second case, we can construct non-Euclidean geometries like the sphere and hyperbola, etc. So that is my question, that in the other universe in which there are sets between the naturals and the reals, hasn't anyone constructed a set of that sort in that space?
No, no,
sir.
because to me it seems like once you construct a set of that kind, you would have finished the debate, right? Okay, so they haven't constructed it. They've just said that this statement is consistent with set theory. Yeah, okay.
So मेरा क्वेश्चन ये है कि आपने लिखा था कि बल्कि हिल्बर्ट ने लिखा था कि नो वन शेल एक्सपेल अस फ्रॉम द कैंटर्स पैराडाइज ये
Yeah.
why he said that?
I think he was just trying to praise Cantor.
Okay.
He probably he thought that foundations of set theory is such a huge contribution to mathematics that he called it Cantor's paradise.
Okay, and another thing, क्या ये कैंटर्स पैराडाइज हम इन्वेंट करते हैं या डिस्कवर करते हैं? The same old question.
Look, I mean, I've heard Edward Witten being asked this question, okay, do we invent mathematics? And he says that we discover it. You know, we're just on a stroll, everything. And you know, Witten is a very, very smart guy, so I'll accept his answer.
Thank you.
Okay, Sarmad, thank you very much.
Okay,
Very nice
thank you.
lecture.
Thank you. So
Thank
kind of you.
Thank
It was lovely. I hope I'll see you next time in the next lecture, and you know, it would be lovely to
Okay,
come
Agya.
again. Thank you.
Why didn't you come?
Well, there's no good valid excuse.
अच्छा,
Just
ठीक है.
yeah.
Okay, all right, bye.
Okay, bye.